好，没有，去年没有。今年就是没有，就你这 AI 还有段路明院士啊，还有段路明院士啊，他可以来啊，他好像是他的报告好像是过了吧。
Okay, let's start. So our last speaker this afternoon is Professor Jiazhong Hu from Tsinghua University. He's going to tell us about observation of universal non-Hermitian dynamics in 1D Latin Gurling.
Hello, everyone. Good afternoon. And in fact, just a few days ago, I realized that I'm slightly different comparing to the previous speaker. Is that I am an atomic physicist, not researching in the particle physics. And our research topic is mainly focusing on the extreme low temperatures, where the typical energy scale is characterized by the nanokelvin, which is completely different end of the physics. Therefore, I changed my slide and talk a little bit, and I enrich some how we did these kind of experiments and observations in order to let all the audience to know what we are doing and what we are thinking and what we are researching. Therefore, at first, I'm planning mainly talk about our recent progress that on the 1D Latinger liquid, which is the strong correlated quantum matters in one dimension. Therefore, and now I'm going to enrich the context that I'm going to start from the beginning about all the non-equilibrium dynamics in the optical lattices to start with, to say about what we are thinking and what we are considering. And this is my outline. And first, I will introduce about the improved band mapping about to measure the quasi momentum in the optical lattice system. Then later, we will start about our conventional approach about the non-equilibrium dynamics based on the Kibble-Rueck mechanism. Then later, we develop a new method in order to probe such a quantum system in non-equilibrium states. First is about the improved band mapping. In fact, our system is very different compared to the particle physics and the cosmology. We make the atoms becomes very, very low temperature, which is on the order nanokelvin and microkelvin, that use the laser to form the standing wave to make an optical lattices to make all the atoms to move and intact in such a synthesizes the lattice systems. Then we investigate about their quantum properties in this lattice system. And the lattice system can be described by such a Hubbard model where we have the tunneling time, the interaction time. Sometimes we will have some inhomogeneous background or the chemical potential effect. Therefore, and for such a lattice system, also it's similar to the solid state system is that what we are interested is about how the momentum, or exactly to say is how the quasi-momentum in such a lattice system. Here we improve the band mapping method. We make the band mapping becomes very, very precisely. What means the precisely is that in the multi-insulator region, we can make all the band mapping, the quasi-momentum measurement becomes very, very flat. It is exactly a square in the first braining zone. And we may compare about the previous conventional method is that, okay, the band mapping of the quasi-momentum distribution is not so flat. Here we can make it very, very flat, which is exactly a square. Therefore, on the one side is very low lattice trap depths where the tunneling can be allowed between different sites, that we have a super fluid state of the atoms, which we have a very sharp peak on the momentum zero states. And on the other hand, when we turn off all the tunneling and then we make the state become a multi-insulator, all the momentum distribution will be uniformly distributed in the first brane zone. This makes us to exactly to distinguish such a quantum state. We can divide it into a incoherent plateau and a coherent peak. That we can say, okay, how many atoms which are coherent and how many atoms which are incoherent, that we can distinguish these two different phases. Therefore, then we started to first want to probe such a many-body dynamics. We first started from the conventional approach, which is the cable-direct mechanism. What does it say about? It is said that if for a gapped system, if we ramp such a system very slowly, the adiabatic theory tells us that the state will always stay in a ground state of such a Hamiltonian. However, if you have a phase transition point, the gap is closed. Regardless of how fast or how slow you ramp a system, when you near the quantum critical point, the adiabatic theory will always fail. Then the cable-direct mechanism says that when you near the quantum critical point, when you near the phase transition point, there will be a frozen region that the system cannot follow your external ramping. That this frozen region is that the region where the adiabatic theory fails. And it predicts that the system will have a relaxation time proportional to the ramping speed with some certain power order. And the power order is decided by the critical exponents. And also the correlation length is proportional to the ramping speed, also with some decided by the critical exponents. This is the first experiment we started to do in order to probe such a quantum critical exponents to see what it will happen. And previously, the theoretical study to suggest that for such a multi-insulator and a superfluid phase transition is that when you probe it on tip, is that you have a particle Hall symmetry, that in this symmetric class that will have the critical exponents equals 0.5 and 1. If you do not have the particle Hall symmetry, then then you will have a mean field universality class which the critical exponents equals 0.5 and 2. Previous experiment has not fully distinguished these two differences because in all the ultra-cold atom systems, that the harmonic trap background sometimes is always introducing some troubles to us. But however, this time the inhomogeneous trapping this time help us to measure out these two exponents in one experiment. Okay, so what our scheme is that to probe such a system from the superfluid, then we increase the trap depth. Effectively, it is turn off the tunneling rate to make the quantum matters from a superfluid to phase transition into a multi-insulator. Because we have an inhomogeneous background, we have a range of the chemical potential, which is the line on the phase plot that we move this line onto the left, then it will start to see the multi-insulator. Okay, our scheme is that we make the lattice trap depths to turn it linearly. We first prepare the superfluid at a very low trap depth, then we turn on the trap depth linearly to trying to make the system into a multi-insulator. Then, as I mentioned, is that we improve the band mapping. For each time is that we can divide such a quasi-momentum distribution into a plateau, which is incoherent part, and into a peak, which is the coherent part. Then we just look at how the incoherent part changes with the ramping speed. We measure the different ramping speed. For the blue line is the adiabatic curve, is that we ramp everything very, very, very slow. If we ramp the trap depth with some certain speed, then the curve will deviate from the adiabatic curve, then it causes difference. Then we can very clearly to see that here is that for such a system, when the system enters the multi-insulator, in fact, we need some relaxation time in order for a finite ramping speed in the quantum state to reach a equilibrium comparing to the adiabatic curve. Then we just extract out this relaxation time. And we see the relaxation time and the ramping speed. We plot it in a log plot that we find it is a line that it predicts that it will follow such a scaling law. Based on the scaling law, the exponents here, then we can immediately extract out that the nu times z equals 1.1, which suggests such a system with a nu equals 0.5 and z equals 2. However, this is not all the stories about here. We can change our view about the previous measurement. The previous measurement is that we compare the things on the horizontal line. We can compare these things on the vertical line to see how many atoms has been excited comparing to such an adiabatic state. It can tell us about the topological excitation in such a system, which is also associated with the correlation length. And here D is the dimension. The dimension is we are in a 3D system, D equals 3. Then based on this measurement, we just measure how many excitation. Then we compare the excitation with the ramping speed. This is our experiment measure the data curve, which is a line in a log plot. Also, we perform the mean field calculation, which is also a line in the log plot, which suggests that there's a scaling law here. And we find the nu equals 0.5 and the z equals 1 here. Then we have to ask that in one experiment, we found two different scaling zones. Is that one thing, in the early time, we measured the excitation. We find that the nu z times z equals 0.5. And in the later time, we measure the relaxation time. We times together, it equals 1. Then we have to ask why. Why such a system will become this? This is because when we have a harmonic trap background, the chemical potential is undecided. It's a range. When you move this line into the left, you will first touch the on-tip phase transition, which exactly have a nu z equals 1/2. And later, when you enter into the deeper multi-insulator, the dominating mechanism of such system is here. Here is on the central part, which is an off-tip phase transition. This is why later the nu z will become 1. We have to say about the Kipp's rule mechanism. It was predicted for the cosmology based on the symmetry breaking mechanism. However, the symmetry breaking mechanism is not the major or is not the dominant reason for such a scaling behaviors. And we have to say this system, in fact, it is decided by how the gap opened for such a phase transition system. When you enter the phase transition point, your gap is closed. If your gap is opened with the order parameter with a linear scale, then here the nu z must equals to 1. If you open the gap is opened with the order parameter with the 1/2 power, then the nu z has to be equals to 1/2. Then for our such an inhomogeneous system, in fact, the gap is first opened with a square root relation, then later it's bent into a linear relation. This is why in the early time we can see the nu z equals 1/2 and the nu z equals 1. Then later, we also, for such a system, we started to extend it, want to extend it into a two-dimensional system to see what will happen. For this time, so we just fixed the z direction, we fixed the z direction trap depth and to ramp such a xy direction systems. We first calibrate all the parameter, all the how many incoherent parts in such anisotropic optical lattices. Then we started to ramp it. And here, the 2D ramping is that we just fix the z direction lattice at a fixed value. We just change the xy value. Then we could imagine that if one direction we fully turn off such a tunneling rates between all the layers, then your system, your atoms will become a two-dimensional atoms, which becomes a few layers of pancakes, and all the physics should be described by the two-dimensional physics instead of the 3D. Therefore, here we find that if the z direction lattice trap depth is very sharp, then we will see a scaling law in the yellow line. If it is very shallow, then it will see a scaling law in the black line. And the black line here, in fact, which the scaling law is the same as a 3D measurement. This is just that if we change the dimension, we will see a scaling difference from the three-dimensional system to a two-dimensional system, which suggests that the dimension is dominating such a crossover behavior. Then we also want to compare for the different z trap depths. We want to see the critical exponents, how it changes, and how the dimension is influenced. Here, this is the 3D region. The critical exponents should be 1 according to theoretical calculation, and our measurement is also consistent with this. And later, when the trap depth becomes very large, it should equal 2/3, and our data is also consistent with that. And we found in the intermediate region, we found that dimension, in fact, is gradually to transit from a 3D system to a 2D system. Therefore, in the middle region, in fact, the dimension we have to see it's not fully well defined in such a system. It's just in the middle of 2D and 3D that we still need more investigation about these intermediate region behaviors. And then later, this is based on the conventional approach about the Kibble-Zurek scaling to measure the critical exponents that we find, for the many-body phase transition, we first measure out the different scalings in one system because of the help of the inhomogeneous background trap. And later, we found that in such a system, we observe a dimensional crossover from 3D to 2D, that there's a continuous transition, and there's some intermediate dimensions which cannot be defined by integer. And we still need some more investigation for our systems. Then later, we want... It's around 100 micrometer. It's about 100 times 100 times 100, about 1 million lattice size in such a system. Later we want to, in fact, to beyond the linear, to want to find some new approach to about the many-body dynamics. In fact, later the two works, we are trying to beyond the conventional linear response theory. Why do we say about that? So first, we want to think about probing a many-body system by ramping. In fact, there's a Kibble-Zurek mechanism. There's also solid bump. Then later here in this section, we develop two new methods. They are all based on the conventional linear response theory, but we go beyond to generalize it first into a non-adiabatic ramping. Then later, we generalize it into the non-Hermitian region, which is governed by dissipation. The first thing is about the ramping system. For Hamiltonian, if we ramp the Hamiltonian, then we have a wave function evolve. How do we calculate the evolution of the wave function? One very intuitive way is that we make the perturbative theory. We expanded the Hamiltonian, then we just calculate the first order perturbative, second order perturbative, and more. Then later for observable, we can calculate the expectation of such an observable. We want to compare for a ramped system the expectation value of such an observable, then comparing to the equilibrium state at this point. And we found that the difference is decided by what? It's decided is proportional to such a green function. Also, this here is the ramping speed of the final point. It is said that if we ramp our system from a starting point to an ending point, and the difference of the observable, which is only decided by how you reach the final point, and it does not care about the intermediate path, how you, or the intermediate trajectory, and how you ramp it. But of course, there's a limitation about such a kind of argument or claim, is that we have to use all the perturbative theory here to support these things. This gives one more constraint, is that we have to ramp all the system very slow. In such a slow ramping system, we find all the parameters. If you look at the observable, the difference is path independent. It's integrability. It has integrability and only relying on the final state, which is, and the difference is proportional to only the final ramping speed. Then we started to do the experiment. We also used the same optical lattice system, is that we started from the different starting point, and we ramp it to the same ending point, but we can ramp it with different ramping speed. And what we measure is still measure such a quasi-momentum distribution. And we use the momentum k equals 0, the how many atoms there, to characterize such a system and such a theory. And we found, okay, then we compare here. This is the equilibrium state if everything is done adiabatically. Then if we, with some ramping speed, if we have a positive ramping speed, we will find the zero momentum atoms increase. And if we have a negative ramping speed, we will find the zero momentum atoms decrease. And regardless of where you started, where the starting point is, that we found all the things here lying on one line. And for different set of data, we can always to fit about the slope of these data. We found that the slope, they have the same value. It is said that everything here is on the linear response region, that when you have a very slow ramping speed. Then, of course, we also tried for different kinds of final states. We want to figure out what decide about the response or the slope of such a linear relation. And we found, okay, only the final states, where you reach the final state, the slope will show very different. When you have a 11 e-recoil final state, the slope is almost 0. When you have here 21, it's also almost equals to 0. Only in the intermediate region. So what is the intermediate region? In this region, it happens the superfluid to the multi-insulator phase transition region. It is said that the linear response theory here, the non-adiabatic linear response theory here, the grain function here, the derivative of the grain function here is only sensitive to the phase transition region. When you in the superfluid region, it's almost 0. When you're in the deep multi-insulator region, it also equals 0. Then it gives a new measurement of this kind of grain function, particularly in this phase transition region, that you cannot do well-defined quasi-particle excitation systems. And this is how we measure that. Then later, we also tried for the different measurement observables. It's always consistent, and I am not planning to explain this slide more detailedly. And for this part, we found, in fact, for the non-adiabatic ramping, we found every response is linear if your ramping speed is slow enough. Then because of the linear, then every observable is that you will have a formula which looks like an integrable, and which is path dependence, only depending on the final state, how large the speed you reach the final state, and the final state of grain function or the correlation function of such a equilibrium state. And also it's a new probe of these equilibrium correlation functions based on the grain functions. That later we also started, this is the major part I was planning to talk about, is that later we generalized the linear response theory to the dissipative region or the non-Hermitian region, is that we can think about for a quantum system, how do we to probe such a quantum system? All the previous mentioned things is that we apply a Hermitian perturbation, then we try to read out. And the Hermitian perturbation is make the quantum system can evolve coherently following the Schrodinger equations. Then, and such a system, the most famous setup is the measuring the resistance and the upper system. And they achieve a very great of success in the experimental physics. Then, for us, we want to think about, we want to change the Hermitian perturbation into a non-Hermitian loss. Can we to see something more different? Because we are thinking probably that in the dissipative region, you will see some correlation functions that you cannot observe in a conventional Hermitian system. And first, let's review about the linear response theory a little bit. Is that for the Kubo formula, a closed quantum systems, when you look at an observable, you are comparing the difference between these two observables. This is the expectation values at the equilibrium state. This is the expectation values when you apply a perturbation. Then the perturbation Hamiltonian and the observable operators, you will have a commutative theta relation which characterized by different terms. By measuring these two differences, then you can characterize these complex correlations. Then the most famous example, I think, is the TKNN formula. Is that based on the Kubo formula, you will find the conductivity equals E squared divided by H times an integer, which is the chain number. This is also linking the topological, this is also the starting point of the topological physics. Therefore, the non-Hermitian linear response is that for our systems, we apply a non-Hermitian Hamiltonian. This is a loss. And we also, this is a noise term which couple the system with the environment. We also, the same logic is that we comparing it to the difference. This is the equilibrium state expectation value without any perturbative loss. And this is the new expectation values once you apply this non-Hermitian perturbative. And you will find, okay, then you will find, okay, this time you will have a new formula about the non-Hermitian linear response. That you comparing to the conventional one, you will find here you have the commutator relationship here characterizing the correlation function. Here you will have the anti-commutator relationship to characterize such a many-body correlation. And this is the major difference about when you apply a coherent evolution or you apply a loss to probe such a different quantum systems. Then later these questions becomes to us, to the experimental physics, that how to benchmark and prove this. Then we started to design experiment in order to support and prove such systems. One thing is we choose is that first what we need to design loss. We want to design a very simple loss. We just for the atoms we shine a dissipation light. The atom will be scatter a photon, then it will escape from the systems. And this is a one-body loss. Then what we observe is we just choose the total particle number here. Then we can put this formula into, or we can put this expression into these formulas. Then one very intuitive result is that If for such a system, we have a well-defined quasi-particle excitation with the Lorentzian spectrum, which can be, which is for most of cases that with the real particles or quasi-particles, whatever superfluid or multi-insulator, they are all described by such a kind of system. And based on this, you will find all the particle number during the loss that they will decay with the exponential function. And this is a very intuitive result that everything is decay with the exponential function. This is sometimes what we will always guess or expect. But however, for a system with strong correlation, such as the quantum critical region or latent liquid or non-Fermi liquid, the spectrum function is not described by the Lorentz function anymore. It has a divergent form that if you put the form here into the formula, then you will find that, okay, the particle number will decay following a stretched exponential. Here, there's an additional stretched exponent appeared here. And it will show, looks like very different comparing to the exponential decay, which is slower than the diffusive model. Then we started to choose a system. In fact, we started to choose a one-dimensional system, the latent liquid. And because why we choose such a latent liquid? Because one-dimensional system is an integrable system, is that most of times that you can use the Bethe answers to analytical to solve such a kind of system. In fact, we first to exactly to solve such a kind of system, how it will behave. There are two different regions for the 1D latent liquid. The first region is the weakly interacting limit. Another region is the Tanks-Gerardi limit. They are characterized by a dimensionless parameter gamma. The gamma here, in fact, here m is the mass, g is the interaction strength between atoms, and h bar is the Planck constant, n is the density of the system. The effective saying is that if you increase the interaction, you will make the weakly interacting system become strong interaction. This is very intuitive. On the other hand, the 1D system has a very complete different phenomena, is that if you increase the density, in fact, you are making a strong interacting system become a weak interacting system. And this is the 1D system, the phenomena of 1D systems. Here, we can in fact choose the gamma here in different regions, that either the free particle region or either the strong correlated region. And we also calculate the eta, the anomalous dimension here, the eta here, with the gamma here, because here the alpha equals to eta minus 1. Then we started to do our experiment. We just generate a lot of 1D quantum gas. We apply a dissipation line, and the gamma can be tuned from 0.25, which is a weakly interacting system, to a value of 5, which is in a strong correlated region. Then this is the very intuitive data of our measurement. This is a half log plot. Here, this is a logarithmic scale, and this is a linear scale. For three-dimensional Bose-Einstein condensate, we find the particle atom decay is exactly a line here. This suggests that the decay of the atom number is an exponential decay. However, for a 1D quantum gas, we find it's not a line anymore. It follows the stretch exponential. Here we have to put this additional alpha here, the stretch exponents, to describe such a kind of a system. Then, on experiment, we want to investigate how it influences such a system. We use this different dissipation lines, different dissipation strengths to shine the atoms, shine the same samples with the same correlated levels. And we find, okay, the decay speed, they have very different decay speed, because if you shine the light very strong, and the decay becomes very fast. But however, if you use the stretch exponential model to describe such a system, you will find that within the uncertainty or within the error bar, all the stretch exponents, they are consistent. They are not one. They are not exponential decay anymore. And if you change this different gamma, different correlation levels, you will find, okay, for such a stretch exponent model, that you find when you gamma increase, the alpha here, the value, it will go down. When the gamma is very small, alpha equals 1, it's an exponential decay. Then when your gamma is very, very large, then the alpha is, the gamma alpha goes very, very small. Then it becomes more obvious deviate from the exponential decay. And we also put the theoretical calculator line here, which is consistent with our measurement and our observation data. And later, we also trying to compare at different temperatures. We prepare the same gamma, the same correlated levels quantum matters, but with different temperatures. But at this time, we also found, okay, the exponent here, alpha, they are also the same values. They are not relying on the temperatures anymore. Therefore, here we can still look at this slide comparing to the left and the right. Here on the left is exponential decay. On the right, we measure out the structure exponential decay. Here the alpha is characterizing the anomalous dimension eta here, the alpha equals to eta minus 1, which characterizes how your system are strong correlated with itself. And here, it also we find this alpha or this eta, this parameter, independent on how strong you induce the dissipation into the system. It is also independent on the temperature of the system. It only relying on this structure exponential decay, only relying on the intrinsic correlation of such a quantum system itself. Not relying on the external parameter anymore. And based on this, we found, okay, we also observed this such kind of stretch exponential factor, which is independent on the dissipation rate, independent on the temperatures. It's also an intrinsic properties, which are only decided by the internal correlation function itself. Also, this is the first experiment to directly measure out the anomalous dimension eta of a 1D quantum gas. And we think that this behavior is due to a very strong quantum fluctuation and a strong correlation. And this is a new observation that first demonstrated. Then I'm going to also add something recent and new, which we are still measuring in the lab, which is the preliminary data of our experiments. It's still about the 1D quantum gas. And first, I want to mention about the many-body localization. And this graph is cited from the Emmanuel Bloch's group, which they demonstrate the two-dimensional many-body localization, and in such a Bose-Hubbard model. And it is very clear when on the left, when you do not have any disorders, if you prepare the atom on the left side, then after a certain time, it will hop into the right and become uniform. If you have a random disorder on such a system, the atoms on the left, on a long-time evolution, it will not fully hopping or evolve onto the right. The left and the right, they are imbalanced, and the system is refusing to thermalize. And this causes such a kind of many-body localization. And our recent experiment on the 1D system is also associated with the many-body localization. But we have something very different and very new. The first thing is that we still use the 1D systems, but this is a longer tube that you will have a very shallow harmonic trap, and based on that we add a very shallow optical lattices, which the lattice is very, very shallow. It's even the lattice trap depth is even smaller than the one recoil energy, or even it's very small comparing to the ground bandwidth. Also, it is saying that all our experiments were based on a continuous model, not a tight binding model, or not a Bose-Hubbard model, not a Hubbard model anymore. Also, we do not have any random disorders. That based on that, we observe a many-body localization effect. Then what do? In fact, we just started to prepare the atoms on the right to make it very centric on one place. Then we let the atoms, then we turn off this red trap, let the atom to slide down. One intuitive thing about it is that if the lattice is very, very shallow. You could imagine the atoms will just slide down in this background harmonic trap. It will do the oscillations. We just define the left particles and the right particles, the relative difference ratio here, the n left minus n right divided by their summation to characterize such a system. Then we will find that there are three major differences behave. On the left is that the atoms is just a slide on this harmonic trap that you will see them oscillation. From top to down, it's 500 millisecond time scales. But once you increase the gradient, then you will find that the atom will start to localize on the one side. It refuses to thermalize into the centers. And we find that the imbalance, it will go to just to a non-zero values that even after 2 second evolution. Another effect is the thermalization behavior is that if we increase the interaction strength become very strong, then it follows the yellow line. It will become very quickly become a thermalized state that all the atoms become symmetric around the trap centers. And we research these things is that first of all, the interaction-free particles, we just trying to investigate if we enhance the gradient, how it will behave. We found that there are three different phases. The first is the oscillation phase, the right is the localization phase, and in the middle there's the oscillation, the mixture of oscillation and the localization. And in the previous titan binding model, it's always predicted that if you increase the gradient of such system, you will always cause the energy mismatch between different lattice sites. And it will always cause difficulty for the hopping between different lattice sites. Then it should increase more localization. However, in the continuous model, it's different. We will find that when we increase the gradient, the imbalance here, it is oscillation. It will first go to localization, then it will bounce back a little bit recover of the non-localization behavior. This is mainly due, also we simulated the same things by the GP equations. In fact, we found that it is in the continuous model, and not only consider the ground band of a lattice system, we have to consider all the bands. It is say that when you increase the gradient, it will cause the tunneling between different bands. This is why such a localization will have a bounce back. And later, we also for measurement of the interaction particle, we also found that when you increase the interaction, the imbalance or the localization effect, it will not immediately go to zero. It will gradually start to thermalize. For example, at here or here, it still has a certain imbalance or certain atoms is still against and refusing to the thermalization, and which cannot be described by the thermodynamics. And all these physics, we are also on the bottom two figures, we are trying to simulate and calculate with the GP equation to give some theoretical guide, and we find, okay, at this 1 second or 2 second scales, all the theoretical tools tells us that the system will always thermalize. However, on the experiment, we found that, okay, they are still against the thermalization effect. Also, comparing to the different gradient, we also found that when you have a small gradient, you will have more localization. When you have a larger gradient, you will have less localization. This is also a counter result against the titan binding model. It is because in such a continuous model, we have to consider all the contribution of all bands that the tunneling can happen from the ground band to the first excited band. And this is why the larger gradient, it will cause more atoms to become to thermalize. Also, in the end, I would like to acknowledge the contribution of my group member and my collaborators. And in all these experiments, we are focusing on the non-equilibrium dynamics of the optical lattice system. Okay, thank you very much.
So what's the parameter? Could you expand more? What's the parameters you tune when you reach different phases of the many-body localization?
Reach what? Sorry.
what parameters you tune when you try to realize different phases of many-body localization?
Here we just increase the laser power here, and we just make if we increase the laser power becomes twice, then the trap depth will become twice. Then the trap, it will just change. And if we increase twice at this location, and the gradient of the force, the gradient of the potential, it also will increase twice.
So what's the interaction here? It's
a particle and a particle, the S-wave scattering between different atoms, the contact interaction.
Thanks.
So I've seen that. I'm a cosmologist, so So people have tried to model this reheating process that I talked about with cold atoms. You know?
Yes.
And then you don't use the potential like this, but you try to make one that is spatially flat and then generate relativistic dispersion relations. Do you know of any experiments like that are underway in China? Or I know that they're trying it in Oxford, I think, but that's not obviously not what you're doing. But just out of curiosity, I was wondering, is there any effort like this?
I think USTC is creating the flatter potential, and recently, but I'm not very sure about whether they are focusing on this point. But they can create a very flat potential that recently they demonstrate the antiferromagnetic phase transition in such a system. I think also probably they will research on this side because they are also measuring the second sound speed and trying to characterize the dispersion relation of such a quantum matters.
Yeah, so you need the flat potential, and exactly you need to somehow mimic in the effective theory the relativistic dispersion relation. Then you can actually, that's like analog computer for the.
Yes.
That's a really
Thank
cool
you.
thing, but okay. So
thank you.
Curiosity, Thanks.
Is there any hydrodynamic regime here? Because you said this alpha is non-zero, then it is non-Fermi liquid and strongly coupled. Is there a regime for hydrodynamics to measure shear viscosity and entropy density?
I think there are two. It's a little bit. I have to say it's a little bit hydrodynamics region, and this part can be this part and this part can be described by the hydrodynamics, and because it's more like a fluid that this is like a fluid with very less interaction, and this is the fluid which they becomes very. Oh, sorry. These two can still be captured, but this one still cannot.
Now,
it's a little bit weird.
Now, in the regime that you say this is a fluid, can you measure the shear viscosity?
Measure, sorry?
Shear viscosity.
Shear viscosity.
This is the
problem. I haven't measured it, but I will think about this thing.
Because in the quark-gluon plasma, in heavy ion collisions, and also in the cold atoms, this quantity, shear viscosity over entropy density, obey a bound. And they show that there is a bound. I was curious that if such experiment is related.
Okay, thank you for your suggestion. I haven't thought about this side, and I will try to see how to measure it. I think it's a very good suggestion to think about.
It was just curiosity. Thank you.
Thank you.
So I have a basic question. So you show the dispersion relation. So first of all, it's particle-like, right? And has a decay width. So there's a Green's function. So what does the decay width mean? So what it decays into?
You mean the atom number decay, right?
I mean, just mean the decay, the dispersion relation, the Green's function.
The
Yeah,
green.
the Green's function. The Green's function you have. So at some point, yeah, like the previous slide.
Sorry.
Yeah. So at the beginning, it's like a particle-like, right? And then in some condition, it becomes
Do you mean this?
the
The
dispersion relation with
or do you mean this one?
yeah, this one. So at some point, it has a decay width, right? So yeah, my question is, right? So you can show that this one.
This is the non-adiabatic ramping here measure the green function.
Yes.
And also this is another is by the measuring by the loss, which is the
This one. Yes, this one.
Yeah.
So here you can see that it's a particle-like, right? So you have some kind of state and its energy is epsilon and with a decay width.
Yes.
So that means it's just the energy is some kind of state, and then it can decay into other state. Right?
Yes.
And so here you have a width.
Yeah.
Okay. And then you describe it as a particle.
Yes. Describe quasi-particle.
Quasi-particle, and the quasi-particle can just disappear. Right?
Yes.
Okay. So when it disappears, its energy goes into what?
Well, it can also for closed system, because the quasi-particles are also interacting with each other. It also can be translated into the other excitation. This is like if you only excite one quasi-particle here, it may collide with the other particles to excite the others appearing.
Okay. And so basically, from this part to this part, at the beginning it's a quasi-particle line.
Yeah.
And here it becomes something like
a divergent form. Yeah.
You can see the fission.
Yeah.
More questions? So if there's no questions, let's thank our speaker again. And let's thank the speakers in all this afternoon section.
穹苍广而横千，物和多容，星云璀璨，黑洞冥冥。观测天象，探问宇宙，基础科学由此萌芽。